Interesting question, right? Like, why can bees see in the ultraviolet and we can't? Then you go, well, it's natural selection. For some reason, this wasn't really particularly important to us, right?
Mhm.
Why can't we see in the infrared and other things can? It's like,
Because the
Yes,
people that could,
it's a fascinating question, right? Obviously, there's some advantage that you have there that isn't there, and even color distinguishing, right? Of something safe to eat, not safe, whatever it would be. I actually go back to this because it's something that I tell all of my students when I'm teaching ionizing radiation and radiological safety. Whatever you say, there's a cultural concern or that when people hear the word radiation, like, what does this mean? It literally just means light is what it means, right? But it's light in different parts of the spectrum, right? And so it turns out besides the visible light that we can see here, we are immersed in almost the totality of the electromagnetic spectrum. There is visible light, there's infrared light, there is microwaves going around us. That's how our cell phone works. You can't, it's way past our detection capability. But also higher energy ones, which have to do with ultraviolet light, how you get a sunburn, and even X-rays and things like this at small levels are continually being like from the concrete in the walls of this hotel. There's X-rays hitting our body continuously. Like I can bring out we can go down to the lab at MIT and bring out a detector and show you. Every single room will have these.
by our body, you mean the 10 to the 28 atoms?
Yeah, the 10 to the 28 atoms, and they're coming in and they're interacting with those things. And those, particularly the ones where the light is at higher average energy per light particle, those are the ones that can possibly have an effect on human health. So we have, it's interesting, humans and all animals have evolved on Earth where we're immersed in that all the time.
Yeah.
There's natural sources of radiation all the time, yet we have zero ability to detect it, like zero.
Yeah, and our cognitive ability to filter it all out and not.
It would
not give
probably
a damn.
overwhelm us, actually, if we could see all of it. But my main point goes back to your thing about fire and self-protection. If ionizing radiation was such a critical aspect of the health of organisms on Earth, we would almost certainly have evolved methods to detect it, and we have none. Anyway, yes.
The physical world that's all around is just
Yes.
incredible. You're blowing my mind, Dr. Dennis Whyte. Okay, so you have experience with magnetic confinement. You have experience with inertial confinement. Most of your work has been in magnetic confinement.
Yes,
But let's sort of talk about the sexy recent thing for a bit of a time. There's been a breakthrough in the news that laser-based inertial confinement was used by DOE's National Ignition Facility at the Lawrence Livermore National Laboratory. Can you explain this breakthrough that happened in December?
Yeah. So it goes to the set of criteria that I talked about before about getting high energy gain. So in the end, what are we after in fusion is that we basically assemble this plasma fuel in some way, and we provide it a starting amount of energy. Think of lighting the fire. And what you want to do is get back like significant excess gain from the fact that the fusion is making more, is releasing the energy. So it's like the equivalent of like, we want to have a small match, light a fire, and then the fire keeps us hot. It's like, this is very much like that. So as I said, we've made many of the, and what do I mean by we? It's like the fusion community has pursued aspects of this through a variety of different confinement methodologies. Is that the key part about what happens? So what was the threshold we had never gotten over before was that if you only consider the plasma fuel, not the total engineering system, but just the plasma fuel itself, we had not gotten to the point yet where basically the size of the match was smaller than the amount of energy that we got from the fusion.
Is there a good term for when the output is greater than the input?
Yes, there is. Well, there's several special definitions of this. So one of them is that if you like in a fire, if you light a match and you have it there and it's an infinitesimal amount of energy compared to what you're getting out of the fire, we call this ignition, which makes sense, right? This is like what our own sun is as well too. So that was not ignition in that sense as well too. So what we call this is scientific, the one that I just talked about, which is for some instance, when I get enough fusion energy released compared to the size of the match, we call this scientific break even.
Break even.
break even. And it's because you've gotten past the fact that this is unity now at this point.
What is fusion gain, or as using the notation Q from the paper overview of the Spark tokamak? Before we talk, using just the same kind of terminology.
Yeah, actually, so the technical term is Q, capital Q.
Oh, so people actually use Q.
We actually use capital Q, or sometimes it's called
Q is taken.
Q sub P or something like this. Okay, so this is which means what it means is that it's in the plasma. So all we're considering is the energy balance or gain that comes from the plasma itself. Mm-hmm. We're not considering the technologies which are around it, which are providing the containment and so forth. So why the excitement and so well? Because for one reason, it's a rather simple threshold to get over to understand that you're getting more energy out from the fusion, even in a theoretical sense, than you were from the starting match.
Do you mean conceptually simple?
It's conceptually simple that you get past one, that everyone like when you're less than one. That's much less interesting than getting past one, because
so there's a really
you start to
threshold
get energy gain,
to get past.
But it really is a scientific threshold, because what QP actually denotes is the relative amount of self-heating that's happening in the plasma. Mm-hmm. So what I mean by this is that in the end, in these systems, what you want is something where the relative amount of heating, which is keeping the fuel hot, is dominated from the fusion reactions themselves. Mm-hmm. And so it becomes, it's sort of like thinking like a bonfire is a lot more interesting physically than just holding a blowtorch to a wet log, right? There's a lot more dynamics, it's a lot more self-evolved and so forth. And what we're excited as scientists is that it's clear that in that experiment that they actually got to a point where the fusion reactions themselves were actually altering the state of the plasma. Hmm. It's like, wow. I mean, we'd seen it in glimpses before in magnetic confinement at relatively small levels, but apparently it seems like in this experiment, it's likely to be a dominated by self-heating. So that
makes it a self-sustaining type of reaction.
It's more self-sustaining, it's more self-referential system in a sense, and it sort of self-evolves in a way. Again, it's not that it's going to evolve to a dangerous state, it's just that we want to see what happens when the fusion is the dominant heating source.
And we'll talk about that, but so there's also another element, which is the inertial confinement. Laser-based inertial confinement is kind of a little bit of an underdog. So a lot of the broad nuclear fusion community has been focused on magnetic confinement. Yeah. Can you explain just how laser-based inertial confinement works? So it says 192 laser beams were aligned on a deuterium tritium DT target